All right, good morning, quantum enthusiasts. In the last few lectures, we've been doing a lot of hard work. We actually got into some pretty technical details of this rotation estimation algorithm that grew out of Grover's algorithm. And that'll be an important tool in the final factoring algorithm. And it hasn't even reached its final form yet. We still have like one lecture where we like make it even like 20% more powerful. But we're gonna put that on pause for a while and take like a bit of a break. We've been working quite hard. And we're gonna have just some more fun in the next few lectures. And it's really gonna be like back to basics kind of today. I'm gonna tell you maybe like one more rule of quantum mechanics that we never got around to studying. And yeah, we'll just talk a little bit about, adding and removing qubits from a system and shuffling them around. So, okay, I'm gonna start with this topic, deleting qubits or measuring qubits. And so far in this course, basically, we only have this instruction extract all or measure all, which corresponds to taking all the qubits in your system, putting them all into some like measuring device and getting an outcome, and then they're all deleted. At one point, we need to add this like little twist where like if you had a qubit and sort of you knew for sure it was like 0 in every part of the state, then you could delete that one qubit or extract that one qubit and nothing much happened. But today I'm going to tell you just the full rule for what happens if you have like several qubits in a joint state and then you just put one of them into a measuring device. And you've got to be able to do this because in physical reality, like each of these qubits corresponds to something like a photon or an electron or whatever. And there's something stopping you from taking like one of the 10 that you have and putting it into a measuring device and seeing what happens. So yeah, I'll tell you what happens. And the good news is like the first thing you could possibly guess is what is the truth. So let's have an example. So let's say we have 3 qubits. We'll call them A, B, and C as typical. Let's say A, B, and C are qubits. And you get them into the following state. And here we go. I'm going to write it out. 0.9000. Okay, we used to write this in words like 0.9 amplitude on A equals 0, B equals 0, and C equals 0, but now we've got some abbreviations. Plus 0.4001 minus 0.1010 plus 0.1100 plus 0.1111. And you see, I only wrote like 8 or 5 terms here, even though there could be 8, while the rest of the amplitudes are 0. And you can check that this is really like a normalized state, just because, well, the square of this is 0.81, the square of this is 0.16, the square of these 3 things are all 0.01, and that should add up to 1. Okay. So that's our state, and it's really helpful to depict them with these like, especially if there's fewer than, let's say, 4 qubits, these sort of hypercube diagrams. So here, because there's 3 qubits, I got a 3-dimensional picture, and I use this convention. You don't have to, but the up-down direction corresponds to A, and the left-right corresponds to B, and the in-out corresponds to C. So this means that like A equals 0, B equals 0, C equals 0. And I'll just write the amplitudes, and you can check if I made a mistake or not. So 0.9, 0.4, 0, negative 0.1, 0.1, 0, 0, 0.1. Okay. All right, so this cube is just a visual depiction of this state here. And okay, so now we're gonna find out like what happens if you get the 3 qubits into this state, and then you, well, analytically or theoretically, you do extract, let's say, C, the 3rd qubit, which really means that these are 3 photons or 3 electrons. You take the 3rd one, C, and you stick it into like a 1 qubit measuring device. So what happens? Well, we know some things about what happens. I mean, this 1 qubit measuring device, it has like a display that can display either 0 or 1. So it has to display 0 or 1, some outcome for C with some probabilities. And then, assuming it's these like destructive type of measurements that we mostly talk about that get rid of C, C's gone, and then there's only A and B left. And they're going to be in some new state. So, and what that state is could depend on what the outcome of C was. Like if C, got measured and the display was 1, then it might change to this state. And if it got measured to 0, it might change to a different state. And these are 2-qubit state vectors, and we need to figure out what they are. Well, I said we need to figure out what they are. I need to tell you what they are because I'm actually telling you, like, out of nothing, a basic law of quantum mechanics. So you just have to accept this. But I think it's going to be very natural based on like this picture. So in fact, yeah, in particular, this measuring device, if we have these 3 qubits over here, like A and B and C. And here's like our measuring device. It's got some like qubit slot in here. And it's got some like LCD screen in here that, 7-segment display that can read out 0 or 1. You stick C into it. What's going to happen? Okay, by the way, think up over here, C equals 0 is kind of like the front face. Okay, if you picture this is the front face for me, I hope you see it the same way as me. And C equals 1 is like the back face. That's where the 3rd qubit is 1. Okay, so let me tell you what happens. Called the law of 1-qubit quantum measurement. Okay, so after measuring C, the probability that the display is 0 is something, and the probability that the display is 1 is something. These two probabilities need to add up to 1. And I hope you can maybe guess, what is the probability that C equals 0? It's going to just be the sum of the squares of these amplitudes on the front face. And what's the probability that the display is 1? It's going to be the sum of the squares of the amplitudes on the back face. And that makes sense because these two probabilities add up to 1 because the total is the sum of the squares of all the amplitudes. And we know the sum of the squares of all the amplitudes is 1. It's a normalized state. So that's it. So this is the total squared amplitude on basic states that have C equals 0. It's like the front face here, and it's the same thing here. Basic states with C equals 1. Okay, so that's the first thing that happens. And now what's the next thing that happens? There's kind of two cases. You have to say to yourself, what happens to so C is going to be deleted after this, and A and B are going to be left. And we have to understand what is the state of A and B. And it depends whether the display was 0 or the display was 1. So you have to consider these two cases, as it were. So I'm kind of continuing the statement. And like conditioned on seeing outcome C equals 0. That's sort of like you pick the front face. We need a new state of A, and the state of A and B. And the state of A and B, you could depict it with one of these kind of diagrams too, except it would just be a 2-dimensional diagram, right? It would be a square. So like we need like a square for the new state of A and B, and we kind of just pick the front face. So yeah, that's it. It's the front face. Now you might say, oh, that's not a normalized state. That's true, but we're fine with unnormalized states. So we'll just leave it at that. So we'll say after seeing the outcome C equals 0, the new, and this is unnormalized, state of A and B is the just want to say like the part of, I don't want to say it in more formal words than this, the part of the old state with C equals 0. You just retain all the parts of the state where C was 0, but then C is gone, so you delete out that 0. And similarly, condition on the outcome C equals 1. Right, which is like if this probability hits, then the new state of A and B is just like this back square, well, with the C equals 1 deleted, because there is no C anymore. Yes, I'll do an example with this example just now, but any question about this? Okay. So let's check it out in this case. Well, let me delete this. Okay, so starting from that state, let's do the measuring 1 first, just for fun. So let's think about the probability that the outcome for C is 1. Okay, well, it's the total squared amplitude on the back face. The back face is the one corresponding to C equals 1, which is 0.4 squared plus 0 squared plus 0.1 squared plus 0 squared, which is 0.17 or 17%. Okay, so if you get your 3 qubits like this, put C into the measuring device, then 17% of the time, like the display here, will say 1. And if this occurs, well, the new state of A and B, remember C is gone now, is, well, it's like the back face. So it's like this picture here, 0.4, 0, 0.1. Again, like A is like up, down, and B is left, right. Or we can write it as 0.4 amplitude on 0, 0 plus 0.1 amplitude on 1, 1. Again, this is not a normalized state. So if you feel like you wish you had a normalized state, then go ahead and normalize it. That's fine. So if you're like more comfortable with normalized states, then you'd say, here, the total squared amplitude is 0.17. So I would divide these by square root of 0.17. And then this squared plus this squared would be like 0.17 over 0.17, which is 1. So you can do that. Or you can not do that and just be like, I'm cool with unnormalized states. Let me just copy this over here so I have some space. Uh, 0.1100. Okay. All right, so let's do the other case. Okay, so the probability, the outcome for when you measure C that you get 0 is it's the sum of the squares and the amplitudes on the front face. So that's equal to 0.9 squared plus 0.1 squared plus negative 0.1 squared plus 0 squared. I mean, it should check out, right? This is 0.81, 0.82, 0.83. So it's 0.83 or 83%. As it better be, because we started with a normalized state, so it's got to be the remainder after 17%. And if this happens, the new state of A and B is this picture. Is the front face. 0.9 minus 0.1, 0.1, 0, which we can write as 0.9 amplitude on 0, 0, minus 0.1 amplitude on 0, 1, plus 0.1 amplitude on 1, 0. This is a new unnormalized state. Okay, so if you like, you can divide it by square root of 0.83 everywhere, but we won't do that.